Tired. All right. We are going to finally figure out how electrons are arranged in an atom. So the arrangement is called the electron configuration. It describes the arrangement of all of the electrons in a particular atom. Each electron will exist primarily in a region that is defined by one of the orbitals. Since every element has a different number of electrons, each has a different or a unique electron configuration, you will be able to identify an element based on an electron configuration. You need to remember that atoms tend to want to be in the lowest possible energy level, so as close to the ground state as possible. The ground state electron configuration for an element is, like I said, the lowest energy. All right, so this is kind of what a electron configuration looks like. This is a picture representation of it. Notice here, it says 1s. The 1 is indicating the energy level. This would be the N value from yesterday. So here N equals 1. S is indicating the shape of the orbital. So the S orbital is what shape? Sphere. Very good. Okay, does that make sense? So then here we are now at N equals 2. And now we are at the p orbitals. There's 3 p orbitals. What shape are the p orbitals?
S.
The dumbbells. Yep, good.
Yep.
And how many potential orientations are there for the dumbbells? It's kind of a hint right here with the number of circles. 3. So there's 3 potential orientations. One orientation will have the dumbbells laying across the x-axis. Another one will have them laying across the y-axis. And then the third one would be the z-axis, which is kind of hard and weird to draw. So as we go up, we increase our energy level. We are also moving further away from the nucleus. Is that making sense? As we get farther away from the nucleus, we have more space to have more electrons. So each of these adds more orbitals, and we can fill in the orbitals with electrons as we need to. So within each of these orbitals, like this guy right here, what is the maximum number of electrons that guy can hold? 2. So this one can hold a maximum of 2. And I think in the video yesterday, I said that we either show them with circles or squares. And then when we fill in the electrons, we do it with arrows. Can I do it with 2 up arrows? No, why not? Opposite spins, very good. That was Caitlin, right? Yes, nice work. So this is the correct way to show this. This one is incorrect in that both electrons are signified to have the same spin because the arrows both point up. So there are a couple, those are pretty much all the rules, but now we just have to apply the fancy names to these pretty simple rules, actually. So the first rule is the Aufbau principles, and it says that all lower energy orbitals must be filled before electrons can be added to higher energy orbitals. So this means that electrons fill in orbitals in a very set pattern in an orderly fashion. So in this 1s orbital, we have to get both electrons in that orbital before we can go into the next orbital. Does that make sense? And before we can increase our energy level. So this is sometimes called the building up principle. So to help us learn the order that the orbitals fill, we have this diagonal orbital filling rule. And so if you follow these red arrows, you fill the 1s orbital first. Then once you do that, you swing back around and go to the start of the next red line. Then we'd fill the 2s orbital. Then you swing back around, and do we go to the 3s or 2p? The 2p will get filled next. And then we make it to the 3s. And then it loops back around to the start of the next. Is that making sense how this chart works? Okay. There will come a point where I won't let you use this chart. And the reason for that is the periodic table is set up in this way. So you can follow it through. And I will teach you how to read the periodic table with this filling rule in mind. But for starters, go ahead, use this chart. It is super helpful, and it will make your assignment fly by as if you know how to read this chart. So for now, go ahead, use this chart, but don't rely on it exclusively. All right, next rule, Pauli exclusion principle says no two sets of electrons in an atom can have the same set of 4 quantum numbers. And then every orbital is capable of holding the 2 electrons. We should notice here that we have our opposite spins represented, one up arrow and one down arrow. Next rule is Hund's rule, and it says orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by its second electron. And all unpaired electrons must have the same spin. So with hydrogen has 1 electron, so we fill the 1s level first, but this orbital won't become completely filled because there's only 1 electron. There's not room there's room for a second one, but hydrogen doesn't have to, so we just leave it open. Helium, however, has 2 electrons, so we fill it the 1s with both electrons. Is this making sense? Okay. Then lithium. Lithium has 3 electrons. So according to the diagonal rule, you fill the 1s with both electrons, and then we can go into the 2s level. So we have to completely fill this 1s before we can put any electrons into the 2s. And so we can't put any electrons into the 2p level, which would be next according to the diagonal chart, until this 2s level is filled. Is that making sense? Okay, it's very neat and orderly. I like it. So let us practice. So Glenville kids, there is an Aufbau principle on Schoology if you want to download it, or do you want me to put it up on the projector? Okay, I will do that. And then you guys can start drawing the orbital filling diagram. That would be the one with the circles or the squares. So this would be like the 1s and then the 2s. Okay, and then start filling in the electrons. You need to know is how many electrons you need to place. So with carbon, how many electrons are we looking at placing? 6? Do we understand that it's 6 over in Leroy?
Yeah.
Yes? Okay. So we need 6 electrons. And so according to the chart, we start with 1s. So we put 1 electron, 2 electron. Then the chart says you go to 2s. 1 electron, 2 electron. Now, with the p's, how many different orbitals does the p shape have? 3. So 1, 2, 3. This would be 2p, correct? Yep. And so we have 4, 5, and 6 electrons. So notice how in the 2p level, we only put electrons into 2 orbitals. Also notice that both of those electrons have to have the same spin. And we have to put all of the same spins in all of the orbitals. So we have to do all the up arrows. So if we needed an electron here, it would have to be an up arrow before we go back and fill in the second electron. Does that make sense? So now to write it out in electron configuration, you take this number here, so 1s, and how many electrons do we have in that orbital? 2. So you put a superscript 2. Then we have electrons in the 2s. How many electrons do we have here? 2. So we write 2s, 2. Then we have electrons in the 2p level. And how many electrons do we have in that level? 2. So there's your electron configuration for carbon. So I could give you this electron configuration and say, tell me what element it is. And all you'd have to go is, all right, there's 2, 4, 6 electrons. It must be carbon. Because the superscripts, they represent electrons. Just the magnesium one and try it again. So how many total electrons are we needing here for magnesium? 12 electrons, okay? So we start with 1s. We have to fill 1s first, so we have to put 2 electrons in 1s. Then Aufbau's chart puts us at 2s. Fill that up. Then Aufbau's charts puts us at 2p. So there's 4 electrons already. There's 5, 6, 7, 8, 9, 10. And then Aufbau's chart says we go to 3s. Oops. So there's only one option here for 3s. So 2, 4, 6, 8, 10, 11, 12. Look at this, writing the electron configuration. So we have electrons in the 1s level, so write 1s. How many electrons are there? 2, so we write 2. How many in the 2s? 2. Then 2p, how many electrons? 2p, 6, good. And then 3s, we have 2. Okay? If we would have done the orbital filling for sodium, which only has 11 electrons, so that would make your 3s only have 1. So it'd be 1s2, 2s2, 2p6, 3s. I know in math class it's really tempting to leave off the 1. That's what they teach you to do. But for electron configuration, you do need to put the 1s in there, okay? So don't omit the 1s. All right, valence electrons. These are the electrons in the highest occupied principal energy level of an atom. So if we look at this configuration right here, the numbers out front, the 1, the 2, and the 2, indicate N, that principal energy level. So what is the highest principal energy level in this example? 2. So N equals 2. So in the N equals 2 energy level, how many electrons are present? 1, 2, 3, 4, 5, 6. Very good, 6. So you have to look at all of the orbitals that are in that second energy level, and then we count the electrons. 1, 2, 3, 4, 5, 6. Because both of these have a 2 out front. Does that make sense?
So anything past the first energy level is valence electrons?
No, not. So Hallie asked if anything past the first energy level is valence electrons. No, it's just in a particular example, the highest number out front. So if in this example down here where we went to 3s, our highest energy level is 3. So we'd have 2 valence electrons here in magnesium. So the word of caution with that, though, is if you look at that Aufbau chart, you'll notice that the farther down we go, we'll fill in like a 3s, and then 3p, and then 4s, and then we swing back to 3d. So sometimes there's a little, it's not a perfect linear 1, 2, 3, 4, 5, 6. You'll have to make sure you're jumping correctly. So then, with this in mind, what element is this? Oxygen, good, because there's a total of 8 electrons. But that would be a lot of work to do, like, to gold, which is like number 79, to go 1s2, 2s2, 3p6, blah, 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 blah. So what scientists came up with is this noble gas notation. And so this is in when you take the elemental symbol for the last noble gas prior to the atom that is written first, followed by the configuration for the remaining electrons. So if we look at sodium, this would be a fine time to look at a periodic table. Sodium is in that first column and number 11. So the noble gases are in the very, very, very last column. So helium, neon, argon, krypton, xenon, radon. So the closest noble gas to sodium would be neon. So what they did here is they put neon in brackets, and then they continue the noble gas, they continue their electron configuration from that. Noble gas configuration is going to be tricky for you without knowing how to use the periodic table to set up electron configuration. Okay, so electron configuration comes in handy once we know how to do this off of the periodic table. So if we write, we'll give it a whirl. We'll see how this goes. Write the electron configuration for calcium using the noble gas notation. So first of all, we have to figure out what noble gas is the closest to calcium. Working backwards, never work forwards. So you have to go 20, 19, 18, so that puts us at argon, so AR. And then how would you go from here? How would you problem solve this? Because I don't know if I know how to teach this without teaching the periodic table part.
I don't know if I know what's going on. Once you find the notation of argon, then let's go from there.
Yeah. So, yeah, let's leave this at this. We'll pick up with noble gas notation tomorrow because I'll start teaching you how to use the periodic table tomorrow because it's nice. It's slick. So we'll just leave this at this. The answer is AR4S2. But we will cross that bridge tomorrow. Does that sound all right with everybody?
Yes.
Okay.